Hi everyone. So in the previous video we talked about the fact that the Bohr model of the atom is very successful, but it's based on this kind of questionable assumption about the discrete nature of angular momentum of these electrons. One way to understand why that's happening is using this de Broglie wavelength. And so now what I'm asking you to do is to throw away the idea of an electron as a particle. And let's talk about it as if it were a wave. And the wavelength associated with that wave is given by the de Broglie wavelength. Okay? So we should, instead of thinking about an electron spinning, we should imagine this electron as a string, if you will, that's vibrating. You know, it's not moving, but like ringing. Okay? Now the ringing is only going to occur in certain types of patterns, right? I can't just have an arbitrary pattern. The pattern has to close back on itself, right? Because it's circular. So, you know, each one of these little packets here represents half of a wavelength in the wave, right? This is a total wavelength, so this is half. I have to have an integer number, right? I have to have a whole number of half wavelengths. Because if I don't, the pattern doesn't close on itself. I don't get a resonant standing pattern like I do when I'm talking about standing waves with strings or with in an organ pipe or things like that. I need a standing wave in order for this situation to be stable. And so de Broglie gives me this connection, which I can kind of buy if I'm willing to accept an electron as a wave. I've got an integer number, a whole number of half wavelengths has got to equal the circumference of that circle. Now, if you go through and do some math, you find that this actually justifies this quantization. This n value here shows up over here in Bohr's assumption. And so the de Broglie wavelength allows us to understand how the Bohr atom works the way it does. Now, this is clearly not right because the atom is a three-dimensional object. So what we really need to talk about is three-dimensional standing waves. Now, the mathematics is kind of complicated, but these are the pictures associated with three-dimensional standing waves. In math terms, they're called spherical harmonics. But you might recognize these from chemistry. These are the atomic orbitals, right? What I'm saying now is that these atomic orbitals, there's nothing really quantum mechanical about them. They are really just three-dimensional wave motion math. And so these are the different patterns, the different ways the electrons can ring when they are sitting around a nucleus. And these patterns are characterized not by one number, but by three. And this threeness is really associated with the three-dimensionality of the standing wave. In quantum mechanics, we characterize them as principal, angular, and magnetic, traditionally given the symbols N, L, and M. And the three quantum numbers kind of do different things, or tell us different things about these orbitals. The N value, the principal quantum number, tells us about the size. How large is that pattern? The larger the N, the larger the pattern. It's really a throwback to the Bohr model where you've got the radius is connected to the this N value. The same thing happens here, that the effective radius of these patterns increase. So, for example, this pattern is associated with a principal quantum number of 2. This one is 3. They're basically the same. They're balls, you know, but one is larger than the other. Here's another example where this one's quantum value of 4. So n equal 2, 3, 4. You can see kind of the patterns associated with them. The angular quantum number changes the shape. So this has an angular quantum number, an L value of 0. This has an L value of 1. Here's an L value of 2. And it's kind of associated with the number of like leaves associated with this. Here's an L value of 3, I believe. Maybe this is it. Anyway, the point is that the different kinds of shape are controlled by this angular number. What about the magnetic quantum number? The magnetic quantum number tells us whether or not that pattern is spinning. Now, I know I told you to not think about these orbitals as moving, that they're actually ringing. But because there's a certain symmetry here, we can have a spin and the pattern stays the same. And so the spin underneath, even though it's indistinguishable from not spinning because the pattern stays the same, it will generate a magnetic moment because we have circular current, basically. And so a magnetic field can distinguish that third quantum number. And so these three quantum numbers are how we characterize where an electron is in the atom. Now, truly, things are four-dimensional. Einstein taught us that with the special theory of relativity. And so technically, there is a fourth quantum number called its intrinsic spin. It's usually given the symbol m sub s. And it only takes on values plus minus 1/2 for reasons that are related to quantum electrodynamics. Really, in a sense, you kind of have this four-dimensional standing wave, which I know doesn't make any sense, so don't think about that too hard. But the reality is, in order to specify the state of an electron in an atom, we need these four different numbers.